So let me just briefly go over Hodgkin Huxley again. So there's dV dt is equal to, and there's actually a capacitance term, is equal to current. Okay, so that's sort of the basic law. And we will actually break out current into different, there's a sodium current, there's a potassium current, there's a leak current, and later on we're going to add in a synaptic current. So we can actually define these currents more explicitly in that they are gating variables. So there's some kind of opening and closing of a sodium channel which is dependent on the voltage and time, because it takes a little time for these ion channels to open and close, right? And that's multiplied by, and then there's some voltage of the cell minus this sodium reversal potential. And the order of these I never remember, so you got to make sure it's the right. And then plus GK, which is also voltage and time, times the voltage minus EK. So this is the potential. So potassium comes across the membrane. If the voltage is close to the reversal potential of potassium, stops flowing. But the further away it is, the more current that comes through it. And then there's one more, the G leak, which is really only is only a function of voltage, V minus E leak. Okay, so but what is this conductance value? This is actually how many ion channels are actually open and closed. And we represent this really as a, we could break this down into some kind of maximum conductance, or let's call this G max. This is if all the sodiums happen to be open. There's some constant, which is essentially, we can think of, there's n number of channels in the membrane, and each one can let a certain amount of current through, and if all of them were open, this is how much current would be flowing through. Okay, and then we have a M, which is essentially what's the probability of any single channel being open. Okay, so that's a probability function, and it's dependent on the voltage, and so there's M, and it turns out there's three voltage-dependent subunits of the sodium channel. So any one of them, all three of them have to be in the open position for them to be open, so it's actually cubed. And then there's an inactivation. So it turns out when sodium channels are open, automatically after a little while, a little plug comes in. It's called the ball and chain model. It comes in and plugs it. This is the rate at which it plugs it, which turns it off. And then we multiply that by V minus E and A. So we need to actually calculate, given a particular voltage, what is the probability of one of the voltages being in open condition state, and also what's the probability of it being in the closed state. Okay, so if we plot M, and we can, the problem is these things, M and H, are functions of time. They change over time. And so we can talk about what would be the number of channels we would expect to see open if we left the held the voltage for an infinite amount of time at that particular value. And we can plot how many channels we would expect to see open given a particular voltage, and we see something like that, where you get something around minus 20 millivolts is the half activation. This is being 0. This is all of the channels being open. So it makes a sigmoid function like that. There's another function that's for Hinf, which goes just the opposite. It looks like this. So this is 1, this is 0, this is voltage, and some half activation. This is H1/2. And then, and similarly, you see a curve that looks like this for potassium. So there's going to be a G max, GK max as a function, which is times H, M, N to the fourth. So there's 4 subunits of sodium, V minus EK, and there's some function for M N infinite as voltage, and it looks something like that. So we need to get to also what is the actual M at a particular time. And so we can actually calculate a function dm dt is equal to, and then there's a m inf minus m over, actually it's m inf minus m over tau m. And similarly, there's a dh dt is equal to h inf minus h over tau h. And we calculate the h infs and h. So it turns out m inf is equal to, was it alpha over alpha m over alpha m plus beta m, something like that, right? And then the tau m is equal to 1 over alpha m plus beta m. And I think in that lecture on Tuesday, which I did through Unite, I go through and derive where these come from. And it's essentially saying that we have the m in the open state and transitioning to the closed state, m closed, or sorry, this is closed state to the open state. And we talk about alpha is the rate of opening and beta is the rate of closing. And we solve these equations to get these guys here, and we plug them in here to get those. And so there's functions which are fairly simple functions of how alphas and betas depend on the voltage. So the rate of opening and closing changes.
So is there no, in a potassium term, we just have n to the 4th?
Yeah, there's no inactivation of potassium. So if you hold it at a particular voltage, all those cells will just stay open. Sodium is different, that you hold it at that voltage, they'll open up, and then they'll close off. So it's a transient. Okay. So, yes?
We have 3 subunits, so we have n to the power of 3. Why don't we have h to the power of 3? Because we have 3 subunits.
Yeah, so the thought, this is sort of the, you actually have 5 subunits, of which 3 of them are voltage dependent. Here, did I draw 6? I guess I drew 6, didn't I? There's a big one. So there's 5 subunits. 2 of them are not voltage dependent. 3 of them are voltage dependent. All 3 of them need to be in the open state for this to open up. Okay, so we have sort of all these channels that are sitting here. Okay, and so there's a pore going down the center, and sodium will flow through that pore. But you also have this ball that's hanging off here. And that ball, when the voltage starts going through, eventually this ball will swing up in here and block the channel and close it off. And so it's this ball is only one ball. It's either in or it's out. Yeah, Joe.
Like, what should we set for the initial values?
That's a great question.
MNA.
Yes. So, in MATLAB, you set these all as a vector, right? And you have a vector which calculates dvdt, dmdt, dhdt, dndt, and then you use an ODE integrator to integrate it. So one of the arguments you need for it is the initial conditions. It doesn't really matter. I mean, you're going to get weird transients at the beginning, and if you want to do things like measure spiking and things like that, you want to let the model settle down for a little while. You run it for a while, and then take a value from that model at the end of that run and use that as an initial condition. So you don't have the transients caused by the settling from the initial condition. I usually pick something which I think is close to the resting potential. So, minus 65. An initial condition for dm, dh, dt, and dn dt is you could start with the m infinities, h infinities, and n infinities solved at minus 65. And then you know that you're pretty close to what is a steady state behavior of the model. Yeah. The value of what? C. Sorry. C is the capacitance of the membrane. And it turns out the capacitance of the membrane is something like 1 microfarad per square millimeter or something like that. So they've defined this, so it really ends up being 1. And they've set all of the coefficients for all of these things so that the capacitance is 1. And so we almost always, I explicitly put 1 over C in this model, but it's almost just always set to 1. Yeah. Any other questions? Okay, so the next on Thursday, Ben He is going to come and give a lecture. It's a little out of order, but it was the only weekend of the entire semester, or the only day of the entire semester he could come and give a lecture. So he's going to come and give a lecture about MRI imaging. No, sorry, EEG imaging. And how many are you in his class at the moment? And you're in his 5,000 level class or 8,000 level class? 5,000. So the 8,000 level class he's going to teach next semester is going to really be about how you take EEG and solve the inverse problem to figure out where the sources are. And so he'll give a very short lecture on Thursday to describe all those techniques and hopefully encourage some of you guys to come. And then after that, we will go through sort of lots of different ways of measuring from the brain, and then we'll also talk about electrodes, electrode design, and then I think we'll have the midterm. And then we'll move on into the really fun part of the class where we start talking about applications and neural engineering. Okay, so I am happy to answer questions tomorrow at office hours, and unfortunately I'm kind of booked in meetings in the afternoon, but please send me questions. But please work together because this first homework, solving the Hodgkin Huxleys, is really, really important. One last thing I want to point out is if you look in the alphas and betas functions, there are values at which if you set, I think you see something like 1 over 1 minus e to the negative v minus something like e1/2 or something like that. So there's some value here that if when v is equal to this value, this becomes 0. Right? And then you have e to the 0 becomes 1, and then you have 1 over 1 minus 1 becomes infinity. Right? So there's several places where you have singularities in the equations. And these singularities are a real problem when you're running numerical integration. Things are going along fine, and then suddenly you get a voltage which comes in here, and you get an infinity, and your equations blow up. And so MATLAB's ODE integrator, ODE 1515S, is for a stiff solver, and it looks for singularities in the equations. If it hits a singularity, it steps around it a little bit to solve around those singularities. So either use ODE 15S, or those are just fine for the Hodgkin Huxleys and everything we're going to need. If you need more precision, there's 2,3S as well. But if you use ODE 15, it will crash. If you are using another integrator in another program like Python, who is it that emailed me about Python? Okay, Andrew? Okay, Andrew's going to try it with Python. So you got to make sure you use a stiff solver. Or you explicitly look in your equations what the voltage is before solving this. And if it is very close to this value, then you actually have to go in and use L'Hopital's rule to solve for what the derivative is at that value. And you can solve that explicitly and just substitute in the solution.